Hello there, Mr. Sutton here. You're joining us for the Pre-Cal Honors 9-5 Extra Practice Number 2 solutions on limits at infinity. To find the limit for this problem, since we're going to an infinity, let's choose our champion and forget about the slower growing terms on each side of the fraction. So in the numerator, we consider only x cubed. In the denominator, we only have to worry about this x squared, since that's the fastest growing function down there. Reducing these, x cubed over x squared reduces nicely to just x, and as x approaches negative infinity, well, x approaches negative infinity. So there we are. To find the limit as x approaches negative infinity on this problem, we consider only the fastest growing terms on each side of the fraction. Upstairs there's only a 25, so nothing to change there. But down here, this x squared grows much faster than the 5. The 5 becomes insignificant as we approach infinity. So we can think of this as 25 over just x squared. Now this is a bottom-heavy function, so that means that this is just going to automatically go to 0. For this one, to find the limit as x approaches infinity, we ignore the slower growing terms on each side of the fraction, choose our champion. So in the numerator, we just have x to worry about. In the denominator, we'll keep the square root around for now, but we can ignore this plus 1, so we'll just have a 3x squared in there. Now, to make our life a little bit easier, we're going to simplify this denominator a tiny bit. I can square root this x squared and bring an x outside the radical. And now I see that I have an x and an x that are going to cancel out, leaving me with just 1 over radical 3. To find the limit as x approaches negative infinity on this one, we just ignore the slower growing terms. Now you have to be careful here because we have a negative 3x to the fifth kind of stuck in the middle here that's growing faster than anything else. So we're not just taking the first term automatically. So we're just going to consider negative 3x to the fifth. Everything else can be ignored. So this is really negative 3 times negative infinity to the fifth. Well, negative infinity to the fifth is just plain old negative infinity. We have an odd exponent on a negative. Negative 3 times negative infinity, well, that reverses the sign to give us positive infinity. For this problem, to find the limit at negative infinity, we choose our champion, ignoring the slower growing terms. So in the numerator, we consider only 2x squared. Denominator, we don't worry about the negative 4. It's just the x squared that's going to matter as we approach infinity. And we can cancel out these x squareds, leaving us with a limit of 2. For this problem, we're trying to find the limit as x approaches infinity of this expression. Now the key on this one is to recognize, since we're going to a positive infinity, this x cubed over e to the x is a bottom-heavy function. E to the x, as we go to positive infinity anyway, is growing much faster than this cubic function up here. Since this is a bottom-heavy piece of our expression, we can consider this to just be 0. So this is really just 0 plus 2, or just simply 2. To find the limit as x approaches infinity on this polynomial, we ignore the slower growing terms. So 2x, negative 7, gone. We consider only negative x squared. Plugging infinity in for just this single x expression, we have negative infinity squared, which just comes out to negative infinity. On this problem, we're trying to find the limit as x approaches infinity of negative x factorial over e to the x. So we have x factorial is a faster growing function than e to the x. This is a top-heavy function. That means that it's either going to be a negative or a positive infinity for the overall result. We're just worried about the sign of this thing. So we just have a negative out in front, meaning this is all going to come out to negative infinity. For this problem, we're trying to find the limit as x approaches infinity of this expression. The key on this one is recognizing that sine of x over x is a bottom-heavy function. X is growing much faster than sine of x, which just oscillates between negative and positive 1 anyway. So that means that this sine of x over x expression can be treated as 0. So we have 0 minus 4, which is just a limit of negative 4. To find the limit as x approaches infinity on this one, we ignore the slower growing term in the denominator. This negative 3, don't care about it. So now we can just reduce this fraction here. 2x to the fourth over 2x squared, that just comes out to, let's see, x squared. And plugging infinity into that just gives us, well, more infinity. For this one, we're trying to find limit as x approaches infinity of sine of negative x. Now, as we approach infinity here, and this becomes more and more negative, so you're going backwards on the sine function, sine just keeps oscillating back and forth between negative and positive 1. So because this oscillates without approaching a single constant value, that means that our limit does not exist. It's not infinity, it's not negative infinity, it's just simply does not exist with no direction. For this problem, we're told that f is a function such that the limit of this function as we approach 3 from the left side is infinity. Based off of that, which statement here is true? So the fact that we're approaching 3 from the left side is telling us we have a vertical asymptote of some kind. So let's go through these and see what we can eliminate. Choice A, as we approach 3 from the right side, the limit is also infinity. Well, that's not necessarily true. I mean, it could be. This could be a converging vertical asymptote, but it could also be a diverging vertical asymptote, where we're going to opposite infinities as you cross the asymptote. So this is not necessarily true. Moving on to choice B, f is undefined at x equals 3. This one's a little bit trickier. If they had given us a normal rational function and told us this limit here, knowing that there was a vertical asymptote at 3 on a rational function would definitely tell us that the function was undefined there. However, since they didn't tell us what kind of function it is, this could be a piecewise function. This could be a piecewise function that's defined at f of 3. They could have a special rule that says, okay, for f of 3, the y value is 2 or whatever you want it to be. So because this could be piecewise defined at x equals 3, we're not guaranteed that the function itself is undefined there. So this is a no, although it definitely was trickier to kind of imagine how we could have a counterexample to that. On the next one, we have graph of f has a vertical asymptote at x equals 3. Well, if you're going to infinity with the y values, there's only one way to do that if you're approaching a constant x value, and that's if you have a vertical asymptote. You could go to infinity with y values as you go to the far left or the far right, but approaching a constant x value and not an infinity, you need a vertical asymptote. So this is a big yes. There's no other way to do that. And then this last one, just for the sake of argument here, graph of f has a vertical asymptote at x equals negative 3. Well, they didn't tell us anything about the limit as x approaches negative 3, from the left, the right, or both sides. Basically, this is the answer choice where if you didn't know what this negative meant, or you kind of mixed it up as thinking this was negative 3, you might pick choice D. But we know this is talking about approaching positive 3 from the left side. So that means choice C then is what we're looking for. So this was a no, and since the only yes was C, we're going with that.